The big ideas we're talking about today, there's conductors as equipotential surfaces, and there's conductors and E equals 0 inside a conductor. And I numbered them 1 and 2, but at the same time, we're not actually going to do them in that order. We're of course going to do number 2 first, the old idea, and then we're going to use that as a connection back to big idea number 1 for today, which is conductors as equipotential surfaces. Okay, so conductors and E equals 0 inside a conductor, we have kind of beaten this to death, both in our last testing section and in this one. And our logic was that inside a conductor, so I guess I'll write this out, inside a conductor, and again the key phrase inside a conductor, E has to equal 0 because otherwise charges will move. And I guess I say since charges are free to move in conductors. Now already I've realized that I've done something dumb in this video. I've used the phrase inside. What I should have been careful to do is not just say inside, but inside really means between the walls of. A conductor, because otherwise my language being a little sloppy there might lead to a misconception. So here's our example. This is supposed to be, let's just say this is a conducting, let's just call it a big thick conducting ring at this point. It's like a conducting cylinder. Okay, so this is like a solid object. I'll make it solid. Okay, if I take a small, or if I take a point charge somehow and insert it into the middle of this thing, you guys know that there's going to be some shifting of charges in that conductor. You know that what kind of charge is going to build up on this inside surface, and then what's going to be shifted to the outside surface. Okay, we know that negative charge will then build up on this inside surface, while positive charge is left on that outside surface. And what that does, I'll put another one there. What that does is it makes it so that the electric field due to this internal charge would have electric field that goes out and passes through this conductor. But what that conductor does is it sets up its own induced field that opposes that. So like this little collections of positives and negatives would make its own induced electric field that exactly balances out this field due to the point charge on the inside, and thus E equals 0 inside, or sorry, I should say between the walls of that conductor. Okay, and that's kind of, in our class now, that's an established fact, that E is going to equal 0 between these walls of the conductor, and then out here you're just going to have regular old electric field due to that point charge again. Alright, same idea here if I had like a big conducting hunk of metal, so like a metal block. I just happen to have a metal block sitting around. If I put it in an external electric field, which is what this is supposed to be, directed this way, then we know that eventually that electric field inside, and in fact basically instantaneously, the electric field inside that conductor is going to turn to 0, because that electric field is going to push positive charges this way, or you can think of it as really it's going to attract negative charge to this side, and that creates an induced electric field that acts this way, so that eventually, this is my E induced, so that very quickly E ends up being 0 inside this conductor. Okay, that part we're comfortable with. Alright, well that is going to play a role, and what we need to do is make sure that we're not violating this, which is an established fact for us, as we talk about big idea number 1 for today, which is conductors as equipotential surfaces. So there are two things that can make charges move. One is an electrical field, but the other is that charges move due to a difference in voltage. Okay, and if you think about that, that's kind of also an established idea for us. If you have a source charge here, and you put a little test charge here, yes, it's going to move, it's going to be repelled away because of the electric field produced by that charge. That's true. But it's also true that that charge is going to move because it's going to move from higher to lower voltage. Okay, so you can think of it as charges are going to move because of that difference in voltage. That's how we're going to explain why circuits, when we get to electric circuits starting tomorrow, why charges move within a circuit. It's because of a difference in voltage between two places. It's also due to this electric field, so the two kind of go hand in hand. It's kind of different ways to look at the same idea. Okay. All right. Well, if we have a conductor, any kind of conducting object, the idea is that that conductor is going to have charges move until it becomes an equal voltage surface. Because if it doesn't do that, well, then you have a difference in energy, and that's what makes charges want to move in the first place. Kind of like water. Okay, so we've had a lot of water around here in the year we're filming this. Why does water not move in a lake? Because in a lake, everything's at the same height. Everything's at the same potential energy. Nothing flows. Why does water move in a river or in a stream? Well, because they always flow downhill. Okay, you've got higher potential energy, I guess, but in our case, we're going to use, in this exact example, potential energy and voltage interchangeably. Water always flows from higher potential energy down to lower potential energy. Now, what makes it do that? Well, there's a gravitational field, just like there's an electric field that makes charges move. There's a gravitational field that makes that water move, but at the same time, it always is going to flow because of the difference in potential, from higher potential to lower potential. Charge does the same thing. So, if we're thinking about a conductor, what that does is it does kind of change things up a little bit. If you have a nice spherical conducting shape like this, and you believe this idea that conductors have to be equipotential surfaces, it explains why charge on that conductor will evenly distribute itself, any excess charge will evenly distribute itself around the outside of that conductor. What it also does, though, is it explains why if you have anything with pointy edges, so let's say you have like our conducting block again, or you have I'll just extend my picture sideways, or you have a lightning rod. I'm going to kind of draw the lightning rod to an extreme. So something with like a pointy tip like I saw everywhere at Disney World this summer. There are lightning rods everywhere at that place. I had no idea. I guess they don't want people to get struck. Makes sense. But in these situations, anything with corners, the charge doesn't spread itself nice and evenly around the outside. Instead, the charge will tend to collect at the corners more so. Not so that there's a funky electric field, but so that this becomes an equipotential surface. So if I'm thinking about what we learned yesterday as far as equipotential lines, if I just start drawing electric field lines around here, I'd have kind of a concentration of electric field lines there. And then as we go around this turn, kind of a concentration of electric field lines where there's more charge collected. But if I want to look at keeping this in equipotential, we learned that the spacing between the lines has something to do with the field strength, but also that equipotential lines are always perpendicular to electric field lines. So my my equipotential lines would look a lot like this. It would be kind of a shape like that. Okay. And as I'm looking at this equipotential line, because it's always got to be perpendicular to these, the only way I can make this into an equipotential surface in kind of an electric field that has this same density is if I have a bigger collection of charge at the edges, at a corner. So in a lightning rod, part of the reason that the lightning rod works is because to make this conductor an equipotential surface, you get a big collection of charge right near this tip. And the lightning's like, well, where should I go? I'm a big hunk of electrical or negative charge. Well, it's all at the same voltage. It's going to strike this point first. because it all ends up being at the same voltage. Okay, it's not a brilliant lesson, but it's enough for us. That's all we really need to know, is that a conductor turns out to be an equipotential surface. All right, I'm going to pause that and see if we have any questions, or if we're just like, nope, I'm good with that. So a good question was just asked about the lightning rod example, because I just kind of went through that quickly. The lightning rod is always neutral, and then as you get this big collection of charge someplace nearby, so this is a cloud, you can't tell what it is, but it's a cloud, and it's got a whole bunch of excess electrons. It's a conducting object, so it's going to shove extra electrons down into the ground and be left with a positive charge. And then that's what's going to help attract this thing to it. Okay, a great question was just asked, what's considered the equipotential surface? The line I drew around, or the surface? I didn't have a way to draw in around there to show that it was an equipotential thing. The outside of this is actually the equipotential surface. I just drew another kind of equipotential line out further. But the surface itself will be an equipotential surface. The question was just asked, once you kind of have the charges shift around due to the presence of something else, is it fair to always say that a conductor becomes an equipotential surface? Yes, indeed. It will always turn into an equipotential surface. Okay, next great question. So did I just draw these pluses on the outside because that's where they are, or because it was easier to draw them there? No, any excess charge always resides on the outside surface of that conductor. Kind of like when we had, because if you think about adding charges to that conducting object, if you think about adding them one at a time, if I put one positive charge on this thing, it'll be here. If I put a second one on, it's going to have to be attached to this object, but get as far away from this as possible. As far away as possible would be on the opposite side and on the outside surface, because those charges, just going back to our basics, would repel each other. So those charges are attached to this object, but on its outside surface.